Having introduced the laws of thermodynamics, in this lesson video we will focus on the most important one in A-level physics, the first law of thermodynamics. It's a simple equation but packs a lot of understanding inside, so pay attention to make sure you really understand what the three terms actually mean. Let's start with the equation. Delta U equals Q plus W. This is important. In fact, it's really very important you get this right because there are two versions depending on how work done is defined. We will only use this version, but if you look at other videos, textbooks, syllabuses, you will see the other version where delta U equals Q minus W. We will only use this. Delta U equals Q plus W. It's a simple equation, and so the maths will not be a problem in most cases. The problem will be in understanding clearly what values to use for Q and W, for heat and work done. Let's start by defining the terms in the equation clearly. The two terms on the right are referring to energy transferred to the system. Q is heat, which is defined as a transfer of thermal energy. So we could say that two objects have thermal energy. I'll make them the same mass. Object A has more thermal energy than object B. Since mass is the same, A must have a higher temperature. So, following the second law and common sense, A will cool down and B will warm up. Thermal energy is transferred from A to B, and that is what we call heat. So, Q is heat and it has a positive value if heat is added to the system we are looking at, and it has a negative value if heat leaves the system. Now please note, this has nothing to do with how energy is stored in the system. It is only saying that we are transferring energy into the system in the form of heat. The other term on the right here is W, for work done. By convention, a positive value of W means work is being done on the system. Energy is being put in. A negative value means energy is being removed. So what we have here are the two ways to add energy to the system, either by heating it or doing something mechanical like squashing it or lifting it or electrocuting it. Work done can be applied by any kind of mechanical method, but in A-level we're most likely to look at changing volume. Those two, Q and W, are not too complicated once you can get used to the positive and negative values. You also need to separate them from what is happening inside the system because that is described on the left of the equation with delta U. In fact, let's separate things with a summary. The equation for the first law of thermodynamics is the simple delta U equals Q plus W. The right-hand side of the equation deals with energy transfers, only the energy transfers. Q is the heat transferred, with a positive value for Q, meaning thermal energy is transferred into the system. W is the work done, with a positive value for W, meaning work is done on the system. Work transfers energy into the system. The right-hand side of the equation deals with energy transfers. And next, we will look at the other side. The left-hand side deals with what is happening inside the system, and at the moment it is simply delta U. Delta means change, so if Q is positive and W is positive, delta U will be positive, meaning the value of U increases. So let's focus on U. U is the internal energy of the system, all the internal energy. Let's imagine a piece of metal. Gases might be easier in some ways, but particles keep moving around. I want a solid piece of metal so it stays still. Well, nearly. Here are the atoms, all lined up as expected. But they are not going to be still, are they? They vibrate, and so they have kinetic energy. So one form of internal energy is kinetic energy. There's actually three important forms of kinetic energy. Vibrational, like this. Translational, like gas particles moving around. And rotational, like an atom spinning on its axis. Those three combine to become the kinetic energy component of internal energy. Now let's look closer at these atoms. They are made of positively charged nuclei with orbital electrons. We have a positively charged particle here and another positively charged particle here. Clearly, there's going to be an electric field generated here, and the particles are going to have electrical potential energy. If I stretch the metal and pull the particles away from one another, the electric field is going to change. The electrical potential energy changes. Without changing how much the particles vibrate, so without changing their kinetic energy, I have changed their potential energy, and that's one aspect of the second element in internal energy. Internal energy U is the sum of the random distribution of kinetic and potential energies associated with the molecules of a system. And that's where we need to pause. Internal energy, U, is the sum of a random distribution of kinetic and potential energies associated with the molecules of a system. The internal energy increases if the kinetic energy of the molecules increases, or if the potential energy of the molecules increases. And we cannot control that directly. What we can do is provide heat Q and work W, then let nature decide how to use it. Sometimes we might provide heat and see the kinetic energy increase. Sometimes we might provide heat and see the potential energy go up. So this simple equation, delta U equals Q plus W, has now been expanded. The right-hand side is the transfer of energy, and the left-hand side is the internal energy, which we now know is the sum of the random distribution of kinetic energies plus the sum of the random distribution of potential energies of the particles in the system. We can control the right-hand side only. We can put in or remove thermal energy. We can stretch or squash objects or other forms of mechanical work. We cannot directly control the left-hand side. Those are material properties. We can try to engineer new materials that behave how we want, but that's it. Water is water, aluminium is aluminium. They will behave as the laws of physics describe. So what do we do? What we can do is make observations and understand what is happening in real-world situations. That's what we will do with the steam engine, to understand how the internal energy changes. But we need a few more pieces of the puzzle first. So far, we have these pieces. That delta U equals Q plus W, where Q is the heat transferred, with a positive value for Q, meaning thermal energy is transferred into the system, and W is work done, with a positive value for W, meaning work is done on the system. Work transfers energy into the system. And that the internal energy is the sum of a random distribution of kinetic and potential energies associated with the molecules of a system.